In 1926, a single equation came along and completely changed how we see the world. In this explainer, we're going straight to the source, the original papers from its creator, Erwin Schrödinger, to really understand one of the most profound ideas in all of science.
A friend actually said this to Schrödinger, and with this kind of charming humility, Schrödinger basically said, "You're right, I had no idea." The discovery felt like a surprise even to him. So what was this idea? What was so clever that it could astonish the very person who came up with it?
To find the answer, we have to rewind a little bit. We have to go back to the puzzle he was trying to solve. A puzzle that had really stumped some of the greatest minds in physics at the time.
All right, so let's set the scene. We're heading back to the early 1920s. It was a time of huge excitement, but also a lot of confusion in the world of physics.
Back then, physicists like Niels Bohr had a model of the atom that, well, it kind of worked. It was built on what Schrödinger himself called customary quantum conditions, which is basically a fancy way of saying a bunch of rules they just had to assume were true. Like electrons could only be in these very specific energy orbits, almost like planets stuck on invisible tracks. But why? The rules just felt random, and that really bothered Schrödinger. He wanted to find a real reason for them.
The spark of inspiration came from the French physicist Louis de Broglie. Schrödinger himself says he was led to his theory by de Broglie's suggestive papers, and the idea was a total game changer. If light can act like both a wave and a particle, well, maybe matter, an electron, for instance, could too. This was the exact clue Schrödinger was looking for.
And that spark led to what I think is one of the most elegant and beautiful analogies in the entire history of science.
Okay, so this was Schrödinger's core insight. He looked at the science of optics and saw a perfect parallel. We know that thinking about light as simple rays is just a handy approximation, right? The true nature of light is a wave. So he wondered, what if the same thing is true for mechanics? What if the physics of billiard balls and planets, classical mechanics, is also just a simplified version of a deeper, wavier reality? In his own words, he put it like this: perhaps our classical mechanics is the complete analog of geometrical optics. He had a hunch that the old rules failed for tiny particles for the exact same reason that simple ray optics fails when light passes through tiny little openings. The path of an electron wasn't a clean line. It was something more. It was a wave.
But look, a great analogy is one thing. To turn this incredible idea into a theory that could actually make predictions, Schrödinger needed a tool. He needed an equation. Before we see the equation, we've got to meet its star player, the wave function, which we represent with the Greek letter psi. Schrödinger introduced this as a new kind of mathematical thing that describes the wave process of a particle. Now, don't think of it like a physical wave in water. Think of it more like a wave of information, a wave that describes the probability of finding a particle somewhere. It's a way of possibility.
And this is it, the famous Schrödinger equation. Now, don't get bogged down by the symbols. The real power here isn't in parsing the math itself, it's in understanding what it does. Think of it like a machine. You tell it the physical setup of a system, like an electron orbiting a nucleus, and it gives you the specific wave function, the psi, that describes that exact system.
And here is where the absolute magic happens. When you solve the equation, you find that only certain wave functions are actually possible. They have to fit the constraints of the atom perfectly, like a key fitting into a lock. And these valid solutions, they correspond to specific discrete energy levels. All of a sudden, those arbitrary quantum rules just vanished. They were simply natural consequences of the physics, like how a guitar string can only play certain notes. Quantization was no longer something you had to assume. It was a result.
So this was an absolutely beautiful theory. But was it right? There was only one way to know for sure. You had to see if its predictions actually matched up with reality.
Schrödinger chose a really specific and tough test case, the Stark effect. This is what happens when you put a hydrogen atom into a powerful electric field. Its single spectral line, the light it gives off, it splits into this really complex pattern of many different lines. The old quantum theory really struggled to explain the intensity of these new lines. So the big question was, could his new wave mechanics do any better?
This is it, the moment of truth.
right from his third paper. That column on the left, that shows the observed intensity from real experiments. And the column on the right, that's the calculated intensity that his equation predicted. I mean, look at them. The numbers aren't just close, they are in fantastic agreement. The totals at the bottom match perfectly. This was the proof. He was onto something huge. But numbers are one thing. This visual, this is just breathtaking. Schrödinger plotted the experimental results, labeled X, right on top of his theoretical predictions, Theor, and it's a nearly perfect mirror image. The pattern, the spacing, the intensity, everything matched. This was the triumph. That clever idea wasn't just a neat analogy anymore, it was a description of reality.
Now, Schrödinger wasn't working in a total vacuum. Another brilliant physicist, Werner Heisenberg, had developed his own version of quantum mechanics at almost exactly the same time.
And the two theories looked like they were polar opposites. Heisenberg's matrix mechanics was totally abstract, built on these discrete tables of numbers called matrices. He basically gave up on trying to visualize what was happening inside an atom. But Schrödinger's wave mechanics, as we've seen, was all about continuous waves. It was intuitive and visual. So how on earth could they both be right?
Schrödinger himself was amazed by this. He wrote, "It is very strange that these two new theories agree," pointing out that their methods seemed fundamentally different. For a moment there, it really seemed like physics had two competing, completely contradictory answers to the same exact question.
But then, in a total stroke of genius, Schrödinger proved it himself. He showed that matrix mechanics and wave mechanics were, mathematically speaking, identical. They weren't competing theories after all. They were just two different languages describing the exact same bizarre and beautiful quantum reality.
In the end, Schrödinger's work gave us so much more than just an equation. It gave us a whole new picture of the universe. He replaced a world of solid particles moving on fixed tracks with a ghostly, probabilistic wave. He showed us a foundation built not on certainty, but on pure possibility. And his clever idea leaves us with this profound question that we are still pondering today. What does it truly mean to live in a world that's made of waves of possibility?